So we already kind of went over some of this, but again, to show you elevation, I want to stress again that the reference surface is there for a visual inspection. It doesn't affect accuracy. The computer uses raw elevation data. But again, it's there to amplify the raw elevation data to allow us to make very easy, intuitive understanding of what's going on in the eye. And again, the most common shape is a best fit sphere, but you can use other shapes. The machine allows you to choose a sphere, an ellipse, a fixed toric ellipsoid, or a best fit toric ellipsoid. Well, why use a best fit sphere? And I kind of said already, a best fit sphere conveys the most intuitive, qualitative information. The differences are only qualitative. As again, all the maps are generated from the raw elevation data. However, to change the reference surface, you have to change all the values, all your normal values, because normal values are specific to a reference surface. Already said that. Okay? So the reference surface does not affect accuracy, sensitivity, or specificity for the computer. It does, however, affect the sensitivity and specificity for us making visual inspections because we don't have the same ability of a computer. So let me kind of explain that. And this is going to be a series of fairly advanced eyes with keratoconus. So again, most of you are familiar with the Belin Ambrosia display. We're going to be getting into that in the second half of this talk. But clearly, if you notice here, this is an advanced case of keratoconus. The anterior surface, obvious positive island. Posterior surface, obvious positive island. Corneal thickness 418, obvious abnormal pachymetric progression. Tonight, it's nearly 10 standard deviations from the norm. So this is going to be a series of eyes with moderate to well-advanced keratoconus. And what we're going to do is we're showing you the back surface. Again, the back surface is the more sensitive, always of greater magnitude. And the upper left is using a best fit sphere. The upper right is using an ellipse. The lower left is using a fixed toric ellipsoid, and the lower right is using a best fit toric ellipsoid. And again, I'm stressing, if you had the same software specifically geared towards any reference surface, the results would be the same, but we're looking at these just to make visual inspections. Okay, none of you would have difficulty missing this positive island. On the ellipse, you wouldn't miss it. You probably wouldn't miss it here. Notice it says left magnitude, but here it's fairly masked. And if you think about it, if you're using a best fit toric ellipsoid, it's going to fit a cone better, and that will mask the cone. Here's another example. Easy to pick it up here. Not quite so sure what's going on here. You can see it here, but again, notice it's of less magnitude and completely masked here. And again, these are cases of moderate to advanced keratoconus. Easy to pick up on a sphere. Not quite easy to see what's going on here. You can pick it up on the fixed toric ellipse, but again, it's of lower magnitude and really masked on the best fit toric ellipsoid. Again, the computer doesn't look at this. The computer only looks at raw elevation data. But for us to make visual inspections, that's a lot easier than trying to look at all these numbers and figure out what's going on. Kind of another example, prominent over here. Here, but clearly masked. You can see it here, but again, lower magnitude. You can see it here, but again, lower magnitude. Another example, here's an astigmatic pattern with the positive island superimposed. Less clear what's going on here. You can see it here, completely masked here. So again, what we're trying to show you there really is for quick visual inspection, I don't care what maps, numbers you use, 90% of the time, I am just looking at the maps quickly visually. And it's very few cases that I actually have to go down and look carefully at the maps. As long as you keep the colors and the scales same and your reference surface the same, you can do rapid, quick visual inspection. That's the advantage of a best fit sphere. So qualitatively, the maps differ. And a best fit sphere gives you the easiest intuitive maps to interpret. Now, the reference surface doesn't change accuracy, but quantitative data, in other words, normal values, are reference surface specific. The reference surface affects the quantitative values, but not the accuracy. If you use a different reference surface, you have to generate all different values, but those values, if used appropriately in appropriate software, should give you identical results. We, again, for the reasons described before, use an 8mm, a best fit sphere, computed from the central 8 millimeters, because that allows the quickest visual inspection. And all our normal values are based on a best fit sphere centered on the central 8 millimeters of the cornea. We did that for two reasons. I said earlier two, but I only gave you one. The first one I gave you is because it tends to normalize the normal asphericity. The other one is because normally for rapid screening, we just display 9 millimeters. It's easier to look at the maps. And this is the area for the 8 millimeter. And we tell our technicians, I don't want to see any extrapolated data. And sometimes you'll see little peripheral. So we chose 90%, close to 90% of the 9 millimeter zone to ensure that we're using non-extrapolated data. So while I just went through the best fit sphere and why we use a best fit sphere, the question would be, is that the best reference surface? And again, reference surface does not affect accuracy unless you're doing something to modify it, and we'll discuss that. Again, to the computer, it doesn't matter. The surface is there to allow visual inspection, to allow us easy, intuitive, quick visual inspection. And this is an example many of you, if you heard me talk before, have seen. I think it's a great example. Okay? When we look at a map of the Earth, we display it against sea level. And if I told you there's San Diego, which is basically at sea level, for those of you who don't know, Tucson is about 2,500 feet above sea level. The Dead Sea is below sea level, and Mount Everest is roughly 5 miles, about 29,000 feet above sea level. If I took the labels off these and asked you to point out Mount Everest, the Dead Sea, and for those of you who knew where Tucson height was, and San Diego, none of you would make a mistake. It's easy, because sea level is intuitive. It's an easy reference surface for visual inspection. I can do the exact same map using the center of the Earth. In that case, San Diego would be 8,000 miles. Tucson would be 8,000 and a half. The Dead Sea would be slightly below 8,000. Mount Everest would be 8,005. And graphically, I took off the names. None of you would be able to tell the difference, because the center of the Earth is accurate, but an inappropriate reference surface for a rapid visual inspection. The computer doesn't see a difference between that and that. But for us, we can make a visual distinction here and not here. So the reference surface, again, is important for visual inspection. Realize that sea level, which is very easy and very intuitive, is not a best fit sphere. It's not taking the whole world and averaging the land, the sea, and the mountains. If we were to use a best fit sphere instead of true sea level, this graph on Mount Everest would be lower, because sea level, again, doesn't represent the average of the seas, the land, and the mountains. If we were to mix those all together, which is a true best fit sphere, that surface would be steeper or higher than sea level, because there's very few things other than Dead Sea below sea level. And that would lower Mount Everest. Well, think about when we're screening for hepatic disease, what we're really looking for are the mountains, Mount Everest. We want to look for the hepatic area. So this is what we currently do. We use a best fit sphere. We average the seas, we average the mountains, and what sticks out is here. What we would really like to do is something more analogous to this, which is what sea level is. It's kind of using only the seas or the flat areas for the reference surface, and allows the mountain to stick up. Again, I want to stress the difference is a visual inspection. So what we've done is, and this is part of the Belin Ambrosia display, is we use what we call an enhanced reference surface. And what we did is we took the standard 8mm zone that we use with the regular best fit sphere, and we've excluded a zone surrounding the thinnest point of the cornea. The thinnest point corresponds to the ectatic region, or quote, the mountain. So what we're trying to do is take the mountain and move it out of the equation. So what we've done is we've taken the same 8mm zone and we exclude a 4mm zone surrounding the thinnest point of the cornea. Now, I say 4mm, it's actually more dynamic than that, and the formula actually will vary the area based on the astigmatism, but the concept is still there. So again, the exclusion zone was chosen by actually analyzing about 1,200 eyes. And as I say here, the actual exclusion zone does vary. It's influenced by the magnitude of the astigmatism, but this is done internally, automatically by the software. So what our goal is to take this reference surface and convert it to this, to make the ectasia or the mountains easier to see. So the goal is to convert this to this, and while that will make the mountains stick up, it's also very important that we don't produce false positives, and what we'll show you shortly is when we do that to a normal eye, because normal eye doesn't have any significant mountains, the map changes very, very little. So let's look at some examples. And it's important to understand what all the circles mean. So again, we're showing you here a 9mm zone. So we're limiting it to 9mm. This big outer circle represents the 8mm zone. So we're using all the data within the 8mm zone to compute the standard reference surface. The dotted lines here are just the pupil. This is now the enhanced reference surface, the same 8mm zone, the same pupil, but this represents the exclusion zone. You'll notice that mark here that represents the thinnest point of the cornea. So we're excluding this area from the reference surface computation. Now, if we look at the regular best fit sphere, you'll notice that we have an astigmatic pattern, but a very early, what looks like a suspicious area here. Looks like a kind of an early positive ion elevation superimposed on this astigmatic pattern. But notice what happens here. It becomes much easier to see. So the enhanced reference surface does exactly what we want it to. It amplifies the ectatic region and makes it easier for us to visualize. Here is another example. I don't think anyone would miss this using the standard reference surface, but notice how it increases in magnitude with the enhanced reference surface. Posterior surface, again, I don't think anyone would miss this, but notice how it increases in magnitude. So again, going from the standard reference surface to the enhanced allows the ectatic region to stand out, just like using sea level allows Mount Everest to stand out better than using a best fit shape of the Earth. Just as important, as I said, are that we don't develop false positives. And this is a normal eye with mild astigmatism with a regular best fit sphere. This is the enhanced, and notice that the pattern looks almost identical. Same thing here, standard, enhanced. So we don't produce false positives. And when we looked at those 1,200 eyes and we compared the difference going from the standard to the enhanced reference surface, normal eyes showed less than a 2-micron average, less than a 2-micron change. And eyes with keratoconus showed an average a 20-micron change. And that a p-value of 0.0001. Posterior was even more impressive. That normal eyes underwent less than a 3-micron change, but eyes with keratoconus underwent almost a 40-micron change. And this is easier to see graphically. So this graph represents the change in elevation from a standard best fit sphere to the enhanced reference surface. As it turns out, this difference is very useful in screening, because obviously this is very easy to separate this population from this population. And that's part of the component of the Belin Ambrosia display, which now leads us into the second part of the talk. What is the Belin Ambrosia display? Well, it's designed to assist you in preoperative screening of refractive surgery patients. And I want to stress the word preoperative and screening. So again, it's to be used in preoperative patients, and we'll explain why later. And it's for screening. Its goal is to help you separate normal from abnormal. It looks at anterior and posterior elevation, both in the standard reference surface, the enhanced reference surface, and then shows you that numerical difference between the two. One of the advantages of the system, of the display, is that the scales and colors are fixed. So once you get used to it, you should be able to look at it and literally in a second screen a patient, because all the colors and scales are held constant. So it allows you to make a quick visual inspection. We show you pachymetric information, the corneal thickness map, pachymetric progression, the location of the thinnest point. It also gives you some quality controls and lets you know when to retake an image. So this was the original Belin Ambrosia, which at the time wasn't called 1, but now we'll call it the Belin Ambrosia 1. Upper left here, this is the anterior elevation using a standard depth fit sphere. This is the anterior elevation using the enhanced, and this is the difference. It's important to understand this lower map is strictly the numerical difference between this and this. It doesn't convey shape. And we all talk about it. I'm going to back up some slides. It may have been easier to understand if we just showed it kind of this way as a bar graph, because people think this is kind of giving you the same shape now. It's not. It's just a numerical number. This represents the posterior surface on the enhanced, and the difference. This is the corneal thickness map, and these are Renato's, Ambrosia's pachymetric progression maps. This is called the corneal thickness spatial profile. I will tell you, this is a much easier one to interpret. This is the percentage thickness increase. And I'll go over this, but I'll go over this again. But this represents how much the cornea thickens going from the thinnest point out to the limbus. And I'll go over this better. And this represents a 95% confidence interval of normal patients and an increase in change. So this is a positive number down below. If the cornea changes more rapidly, the red line will come down here. If the cornea was the same thickness from the center to the limbus, this line would be flat. So this is not as intuitive. This is just much easier for screening, and this is what I'm going to be discussing about later. So that's here. What is the value of looking at the pachymetric progression maps? Well, the value of the pachymetric progression maps is that you can have a normal cornea that is thin or an abnormal cornea with the same central reading. Example, an analogy would be you have two people, they both weigh 150. Is that normal? Well, depends. If the first person is 4'11" and the other one is 6'4", the answer will be no. So here, if you look at the one above, these are two corneas with the same, if all you had was an ultrasound, the same apical reading. Notice this graph. This is that percentage thickness increase. It's right down the middle. So this is a cornea that has normal pachymetric progression, normal progression from the thinnest point out to the limbus. This cornea, while it has the same central reading, notice the pachymetric progression, way below that normal interval. This is a cornea that's changing more rapidly. This is an eye highly suggestive of keratoconus, even though if we look at the same just apical reading with an ultrasound, they would read identical. Both these corneas are 150 pounds. One of them is 5'2", the other one is 6'4". It doesn't mean they're both normal. So that's a big advantage of looking at pachymetric progression. These are two corneas. We're kind of alluded to. Remember I told you before if the cornea was kind of the same thickness, you would get a flat line? Notice the tracings here. They've actually elevate. They're fairly flat. That's because these corneas are edematous. And when a cornea gets edematous, it actually increases in thickness in the center more than in the limbal region, and you lose the normal pachymetric progression. So if you see a flattening of the line right here, that's usually indicative of corneal edema or early endothelial decompensation. Take a drink for a second. So we took what was the original display a number of years ago and then came out with the Belin Ambrosia 2. And what the Belin Ambrosia 2, in addition to just allowing a visual inspection, is that we incorporated a regression analysis to look at the data beyond just making a visual inspection. So we actually looked at not just qualitative, but quantitative information. And the Belin Ambrosia 2 looked at 5 parameters, what we call DF, which is that change in elevation going from the standard reference surface to the enhanced on the anterior surface, and then DB, which is that change in elevation on the posterior surface. We also looked at the pachymetric progression. The pachymetric progression is a single number that reflects this red graph. We also looked at what was the thinnest point, in other words, what was the reading at the thinnest point of the cornea, and then where the thinnest point was displaced in the vertical direction. And each of these parameters were independently calculated based on normal population. So each of those parameters are reported as a standard deviation. So if you were to look here at the bottom, you'll notice that the anterior surface, that change represents a change that's roughly 1.66 standard deviations outside the norm. Notice the back surface, 3.4, pachymetric progression, thinnest point. A minus actually means it's very normal. And this is displacement of the thinnest point. The numbers that we report, we color code just to call your attention. But really, we don't want you to spend a lot of, we don't want you to kind of just spend too much time worrying about the colors. But the independent parameters, each 5 parameters will turn yellow when it's at 1.6 standard deviation from the norm, and red when it gets to 2.6. The reason we kind of tell you the colors are just to kind of make you look, but if it was 1.59, it's going to be white. If it's 1.6, it's yellow. There's no significant difference between the two, so we do want you to pay attention to the actual numbers. Then there is a final overall reading number, which we call the big D. In essence, think of that number as a standard deviation, but it's technically not a standard deviation because it's based on a regression analysis of the 5 parameters that are not equally weighted. In other words, we put them in a formula, but each of these have a different weighting. And what you'll quickly see is that the location of the thinnest point is the least weighted parameter. And again, that final reading is color-coded yellow and red, but again, it's very important to look at what the number is. So, confusing but very informative slide. So, this represents the anterior elevation on the standard reference surface. This represents with the enhanced reference surface. Again, you'll see this represents the exclusion zone. That dot represents the pupil. And what you'll notice here is this other circle seems a lot smaller than I showed you before. It's not at 8 millimeters. Well, it's not at 8 millimeters because you don't have adequate coverage. And that's why you have this big red box here that's showing you a number that's 5.17. Excuse me. That's telling you right off the bat that you don't have enough coverage to allow an 8-millimeter zone to be utilized. And this big red is letting you know you should retake the image. You'll even see on the back surface is only 4.54. So again, I picked this map specifically because it's bad. This patient was kind of either had ptosis or was blinking, but this is letting you know you have to retake it because this is an invalid map. It's only utilizing this tiny area here to compute a best fit surface. Again, this is the corneal thickness map, and you'll notice again that if you don't have data on the anterior surface and posterior surface, you can't develop a corneal thickness in that area. And here are the pachymetric progression maps. Well, I also picked this map for another reason, because sometimes, particularly in abnormal eyes, because the patients are so sensitive, no matter what you do, you can't get a full 8 millimeters of coverage. Well, regardless, you would be able to look at this map. Excuse me, got to take another drink. You would be able to look at this map and immediately exclude this patient from being normal. In other words, this is clearly an abnormal eye. Why is that? Well, even though you don't have 8 millimeters of coverage here, and you don't have 8 millimeters of coverage here, so this is not valid and this is not valid. Corneal thickness can only be generated if you have both anterior and posterior data. So if you look at this graph here, when the line is solid, that's telling you you have anterior and posterior data all throughout up to this point. Then it becomes dotted. But from this point back, this is valid information. And you can immediately see, even from this area back to the center, it's highly abnormal. So yes, I would try to re-image this person, but I immediately know that this person is not a normal eye and is excluded almost immediately based on this pachymetric progression, even though it only goes out to this point. So let's look at some examples. We're going to show you a 4-picture composite, then followed by the Belin Ambrosia display. So real quickly, if I was to do this real quickly, this looks like a pretty normal eye, a little bit of thinnest point displacement here. We look at the Belin Ambrosia 2, everything is normal, but notice we have a yellow on the displacement of the thinnest point. But notice the final overall reading down here, it's actually minus means it's a very, very normal eye, even though we have a yellow here, because again, that parameter is a very low-weighted parameter. Here's another example. It looks pretty normal. The one thing you can't do easily, most people can't do easily, is look at this the corneal thickness map and determine pachymetric progression. But if you notice the Belin Ambrosia, this pachymetric progression hovers down at the lower line here, and you notice the pachymetric progression is 1.71 standard deviation from the norm. Pachymetric progression is a fairly weighted parameter, and that actually gives us a final reading that's nearly 2 standard deviations outside the norm. The advantage of this versus just looking at this, as I said, a lot more parameters than we normally just have by doing a quick visual inspection. Here's an eye where we have a significant displacement of the thinnest point. You can see the thinnest point here is displaced significantly, but everything else looks pretty normal. And notice in the Belin Ambrosia, we actually have a red over here, but again, a completely normal. Matter of fact, if you look here, we're getting a flattening of this graph, which means it's clearly not ectatic, and a completely normal anterior and posterior surface, even though we have a red here. Here's one that looks like maybe we're getting just early beginning of a posterior island over here. Kind of maybe, maybe not. And if we look at the Belin Ambrosia, that's exactly what we see, just kind of a yellow here on the posterior surface. But everything else looks pretty normal. And actually the tracing here, if anything, looks like it may be a little bit flatter and a completely normal reading. Something you should know, it is not uncommon that if you see a slight flattening of the TTI graph, you may see some early changes on the posterior surface. you see that associated with a slight flattening here, that's actually usually very normal, and you get a normal reading here. Here's one where we have pretty obvious or significant posterior island or posterior ectasia, in spite of the fact that everything else looks pretty normal and actually looks like a very thick cornea. And notice again here, we have a red on the posterior surface, and a slight dipping down of this graph, but notice the final reading of 2.45. Now, while that is yellow, realize if it was 2.6, it would be red. To me, this is a highly abnormal map, in spite of the fact that it's a thick cornea. And this is an eye of advanced keratoconus. You don't really need anything more to tell you that, but if you look at the Belin Ambrosia, you'll notice I picked this for a specific reason. Notice way outside the normal limits, red, 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 red. Tracing way below, huge red areas here, a thin cornea. But one thing you'll notice is the ectasia is fairly central. It's a nipple cone. It's fairly central. And notice the displacement of the thinnest point is normal. It's white. But the overall reading, obviously, is a reflection of all the other abnormalities. It is over 17 deviations from the norm. So what's new in the Belin Ambrosia 3? Well, there's a new regression analysis and new parameters. We added 4 additional parameters, and we'll show you why we added those. We added the actual elevation at the thinnest point of the cornea for both the anterior and posterior surface. We added Kmax, and we added what's called the Ambrosia relational thickness. That is the thinnest point of the cornea divided by the progression index. It's a combined parameter. The other thing we added was we added a separate hyperoptic database. We also gave you the ability, for those who want, to turn off the colors on the individual parameters only, not the final. The reason for that is there are some people, for medical, legal, or just their own reason, do not want a map of a patient that they took to refractive surgery, even though the overall reading is white and normal, to show a yellow or red in any parameter. And I can understand that. So again, we showed you one where the displacement of the thinnest point was red, but the map was completely normal. But again, they don't want to ever be in a position where someone holds up and says, well, doctor, why is this red and why did you proceed? So we give you the option to turn off the individual colors, but you cannot turn off the final overall reading. So why did we put on a separate database, normative database for hyperopes? And this is the reason. And really, the only change is on the posterior elevation data. And this is our published data. But if you look at the posterior elevations at the thinnest point for myopes, for 2 and 3 standard deviations, it is 13 microns and, well, rather 18 microns. So that represents 2 and 3 standard deviations from the norm. In hyperopes, those numbers are 22 and 28. Significant difference. So surprisingly, other parameters, including pachymetry, which surprised us, really were not significantly different. That did not require a separate database. But the posterior data was significantly different. So when you check off hyperope, it adjusts a database for the posterior information. Now, we say normal, which obviously shouldn't be normal, and hyperope. I want you to understand, you are to check hyperope on any patient where any axis is positive, which means hyperopes, simple hyperopia, compact hyperopia, and also mixed astigmatism. So if any axis is plus, you ought to check off the hyperopic database. So the bad 2, we already told you, utilized 5 parameters, but the bad 3 added, again, 4 additional parameters: front and back elevation at the thinnest point, the Ambrosia relational thickness, and the maximal sagittal K reading, or K max. So let's look how these all perform and why we did that. So when we do the regression analysis and when we look at parameters, what we're really looking at is what are the individual parameters' ability to separate normal from abnormal? What's their sensitivity and what is their specificity? And the way we can improve on any individual parameter is to use multiple parameters. And we kind of know that from glaucoma. If all we used was IOP, we know IOP is important, but it turns out that it's not overly sensitive or specific. And if we look at cup to disc, it's not overly sensitive. But when we start combining IOP, cup to disc, family history, nerve fiber layer, all the parameters combined, we improve sensitivity and specificity. And that's the goal behind any regression analysis. So this is DF. This represents the change in the anterior elevation. And you notice it has, I'll do this quickly. Notice this is the area under the curve. That's what you're looking for. The more it goes to this point, the better it is in simplistic terms. So sensitivity of roughly 0.86, specificity of 9. This is the back surface. You'll see the tracing. Here is pachymetric progression. And this is the thinnest point, the actual value of the thinnest point. And this is the location. And notice immediately when you see the location at the graph of all the parameters is the worst. And again, that's why that is a fairly low-weighted parameter. But when we combined all of them in a regression analysis, this is what we call the final area under the curve. And it had a sensitivity of 0.92 and a specificity of 0.94. For those of you who have done any kind of work in the past on this type of regression analysis and graphs, as you get closer and closer to 1, it becomes incrementally more difficult to make improvement. So what we looked at is we looked at additional parameters. Again, anterior, posterior elevation at the thinnest point, Kmax, and Ambrosia relational thickness. Additionally, when we set up the regression analysis, we did some additional subpopulation testing on so-called unilateral keratoconus and also patients that developed ectasia. So the additional parameters, this is the absolute value of the front elevation at the thinnest point. You'll notice, again, sensitivity and specificity. Here's that same elevation at the thinnest point on the back surface. Here's Kmax, and again, I'm not a big proponent of curvature, but you'll notice that Kmax also has a fairly poor area under the curve tracing. And here's Ambrosia relational thickness. And this was the final new AUROC curve for the Belin Ambrosia version 3. Had a sensitivity of 9.4 and a specificity of 0.94. And if you can compare the two, again, it looks like it's not a big change, but this actually represents a very large change when you get to this area. So blue represents the tracing for the Belin Ambrosia 2, and 3 represents, here it's called 3.4. We went through lots of iterations. So this represents the current Belin Ambrosia 3. So again, I want to stress that it's very difficult once you get in this area to make incremental improvements. Additionally, I alluded to that we did a study on a subpopulation. So these were 31 eyes that were all had all had obvious keratoconus in one eye, but were viewed as normal with the Magellan and the Navigator software. So these were viewed as, quote, unilateral keratoconus. In other words, the other eye, the eye not supposedly so involved, was read as completely normal. And we also had 11 cases of post-ectasia that were viewed normally with the Magellan preoperatively. And all of those cases were detected by at least 2 of the parameters, and it had an area under the curve tracing of 0.976. So had they used the Belin Ambrosia 3, they would have actually identified these cases as abnormal. So let's look at the new display and some of the features of it. Again, some of it hasn't really changed. This is anterior elevation standard, enhanced the difference, posterior standard, enhanced the difference. But we've added, you'll notice here, Kmax. You'll notice here we've added what's called front elevation at the thinnest point. Here is back elevation at the thinnest point, and here is Ambrosia relational thickness. Notice the numbers on the bottom still stay the same. However, we incorporate all these in the regression analysis, and we actually color code many of the parameters. So there wasn't enough room to fit 10 parameters down below. So these are still the same 5 initial parameters, but again, we notice here, Kmax, thinnest point back, thinnest point front, Ambrosia relational thickness. These are the progression indices, and all of them are reported in standard deviations and are color-coded. You will also notice that everywhere you look on the map, and it may be a little hard to see on this one, but are these little yellow triangles. And I think I'll show you a close-up in a second, right there. These yellow triangles. If you were to put your cursor over the triangle and right-click, I think it's a right-click, it opens up a drop-down menu that will explain what those parameters are. And these are all over the map. So if you ever have a question, the first thing to do is just go to the map. Obviously, not the printout, got to be on the screen. Right-click on this, and it'll drop down and explain what those parameters are. So again, you'll notice all these little yellow triangles all over the place. They're actually sometimes even hard to see where they are, but they're all over the place. And they're all over here also, and they'll give you, they're here, they're all over. Everything has a drop-down menu. So this is an example of why we added the hyperoptic database. So this is a patient who actually has a hyperope in the Belin Ambrosia 3. So anterior, posterior, again, corneal thickness, pachymetric progressions. But notice there's maybe what looks like an early island here, and it kind of shows up a lot more here. But notice when we look down here, everything is completely white, and the final reading is 1.38, well within the normal range. But if I was to use that same patient in the, quote, other database for myopes, this is what happens. The posterior surface turns yellow, and my final reading turns out 1.66 standard deviations from the norm. So on the Belin Ambrosia 2, or if you don't properly check off hyperope, you will get an abnormality on the back surface, but in actuality, that's well within normal range. So again, I want to stress that if you have a hyperoptic patient or a mixed still patient, you want to make sure you check off the hyperoptic database. I also said that you have the option to turn the colors off for the individual parameters, and this is an example why it's really up to each individual practice how they want to do it. This was an eye that had a yellow, but a completely normal reading. And you remember I told you if you have a slightly thick cornea and maybe a slight flattening, which you can see here, you can get little change in the posterior surface. So this is really a completely normal eye, but some people don't like the fact that there's, quote, a yellow here. So you have the ability to show it that way, and you have the ability to turn the colors off. Notice that it doesn't change any of the numbers. We still tell you it's important to look at the numbers, but you have the ability to turn off the colors. So in conclusion, the BAD 3 demonstrates incremental improvement over the prior versions. It utilizes, we say 3, actually 4 new parameters, because the elevation thinness is both anterior and posterior, Ambrosia relational thickness, and Kmax. It demonstrates the ability to detect early keratoconus and ectasia risk that had been previously missed by conventional placebo technology. It's important, as we talked about, that you may have individual yellow or even an individual red, but an overall reading that is well within acceptable range. And also, no map by itself makes a clinical decision. You need to look at the age of the patient, the ablation depth, family history, and put it all into a comprehensive picture. It's also important to look at both eyes. You can't have one eye that's abnormal and consider doing the other eye. Keratoconus is not a unilateral disease. It's also something that hopefully we're going to incorporate in the future. It's important to look at asymmetry between the two eyes. And highly asymmetric eyes should be a red flag also. So it's always important to look at both eyes. It's also important to know that the Belin ambrosia is for preoperative screening, not for postoperative evaluation. Why is that? Well, next slide. You can't use that display really to look at postoperative because, first of all, after an ablation, you've altered the anterior surface. So the anterior surface, again, the Belin ambrosia uses a normative database. You've altered the anterior surface. You can't look at the pachymetric map because you've thinned the cornea. You're going to clearly have an abnormal corneal thickness, an abnormal pachymetric progression. You've thinned the cornea. There is one part of the map you can use, and that is you can look at the posterior surface because the posterior surface normally does not, I want to stress the word normally, does not change. And this is an example here of a 4-map composite post-ablation. Looks fairly normal. This looks normal. This would be kind of a normal, could be a normal corneal thickness map, but you should not see this postoperatively. This is a posterior island. Okay? Now, if I don't have preoperative information, this means one of two things. The patient's either developing post-LASIK ectasia or this was present preoperatively and missed because of inappropriate or incomplete screening. This is a more advanced case. You'll notice here, this is an ablation. So again, you can't tell whether this is normal or not because the anterior surface has been ablated, but you should not have changes on the posterior surface. The absolute best way to look for post-LASIK ectasia is to compare preoperative to postoperative posterior data. The problem often is that you don't have the preoperative data. But if you do, the best way to do that is to use the compare two exams. And there you take the postoperative data here, you subtract the preoperative data, and this is what you normally should see. All these zeros and ones and zeros. Basically, there's no change because you normally should not get changed because you're changing the anterior surface, you're changing the pachymetric progression, you're changing the corneal thickness, but you shouldn't be changing the posterior surface unless you're developing ectasia. So this is a post-op minus pre-op. Posterior, notice, here it is, elevation back, and the change shows almost zero. Compare that to this. Posterior, pre-op, notice this. Big ectasia here. This is a patient who's developing post-LASIK, doesn't develop it, the patient who has post-LASIK ectasia. Now, what can you do if you don't have preoperative data? Because a lot of times we don't have preoperative data. You can use the Belin ambrosia display, but this is the only part that you can actually look at. Because anterior surface, again, you've surgically altered, corneal thickness you've altered, pachymetric progression altered, the posterior surface can be looked at. The only limitation of this, it can tell you if it's abnormal, but it can't tell you is whether it's post-LASIK ectasia or whether it was subclinical keratoconus that was missed on preoperative screening. So the posterior surface is the place to look for early postoperative change and post-LASIK ectasia. So similarly, what's the best way to document ectasia progression? It is the posterior elevation. It is the one that is the most sensitive to change. If you're following patients with keratoconus, similarly, posterior elevation is the measurement least affected by pre-surgical treatments. Contact lenses can affect the anterior surface. And again, for those of you who, most of us don't have access to cross-linking, this is important because the goal really is to pick up these cases early and stabilize them before they get changes on the anterior surface. So key points in closing, preoperative screening requires a comprehensive evaluation of both anterior, posterior, and pachymetric progression. Postoperative ectatic change is best examined by looking for changes on the posterior surface. That the new Belin Ambrosia 3 shows high specificity and sensitivity. I personally don't think any additional testing of placebo is needed. It doesn't really add anything, but it's always important to have additional clinical information, age, ablation depth, family history, stability, and to remember to compare both eyes for symmetry. For those of you who are interested, we do have a second edition of the book out. I do not get any royalties from the book, so I'm not, but it's actually very easy reading, and most people who have read it seem to enjoy it. And again, to remember about the cocktail reception, and way in advance, since I'm representative of the Cornea Society, World Cornea Congress in April of 2015 in San Diego. And I want to thank you all for your hour-and-a-half attention. So I guess we have some time where we can field some questions.